Thank you once again, everyone, for joining us today. My name is ARvind Krishnan, and I work as a simulation specialist at GoEngineer. I work out of the Dallas office, but support all of our different regions, including Texas, California, Utah, and today's webinar, we're going to focus on flow simulation, and more importantly, focus on thermal analysis for a lot of electronic components. So it's the age of the Internet of Things, what they call Industry 4.0, where devices are connected, they're simpler to use, but what that means from a designing perspective is that they're more complicated to design on the back end. We have Alexa, we have Google Home, and all of these are devices that control other things, and that means other things need to have electronics in them as well, which means they produce heat, right? And we want to make sure that this heat is properly ventilated out so that the components don't get too hot, and that's kind of the goal of why this is becoming increasingly important. Apple just released the new A12 Bionic chip, where they spoke about a new manufacturing process that produces 7 nanometer level components. Long story short, they can pack in more transistors into their chips that can do more. But as these devices get more and more complicated and increasing capabilities, you want to make sure that the heat that it produces is appropriately dissipated. Today we're going to look at just a electronics enclosure, and one thing that I wanted to highlight straight away is the model on the right, which is a SOLIDWORKS model, is a lot simpler than the model on the left, which is a real-world example. There are a couple of slots on the top that we're going to model as well, or we're going to take into account in our analysis. You see some circular holes in the bottom, which is the far side in the SOLIDWORKS model, and there are a bunch of components: heat sinks, CPUs, RAM, PCB boards, capacitors, ICs, chips, and we're going to talk a little bit about all of these and how we can do a thermal analysis on these. So for today, we're going to use the simplified model, and some of the conditions that we have set for this is that the CPU temperature, which is in the bottom of the heatsink, has to be a maximum of 68 degrees. The IC packages, which are on the right corner end of the enclosure, close to the exits on the far side, can go up to about 95 Celsius, and we have the RAM chips on the PCBs, which can go up to about 60 degrees Celsius, and these are conditions that have to be met, and we have control over a few things. We have control over whether the fan is an inlet fan or an outlet fan. So in this case, our fan is going to be external, and we're going to use the heatsink. One of the configurations is going to use the heatsink that you see on the model on the right. We also have a second heatsink configuration where we have cylindrical extrusions as compared to slits like they are right now. And finally, currently you don't see the slots modeled on the very top of this enclosure, which allows heat to go out on the top. Do we need those slots or not? So we will go ahead and evaluate them as well, and kind of evaluate the performance of both of them. So obviously I am going to use SOLIDWORKS Flow Simulation for doing today's analysis, which is the major topic that we want to show. The benefits of simulation. What we're going to do today is run about 10 or 11 different scenarios and quickly simulate them to get a good idea of what performance would be better than the other before we go into testing. Again, with a lot of components this small, producing heat, the strategic positioning of your fans, of your exits, of your heat sink is very critical to your design. And we're going to use Flow Simulation's capability to do full-blown CFD analysis to understand this behavior. So Flow Simulation can do both internal and external analysis. In our case, since the flow is inside the enclosure, we're going to do an internal analysis. Also, we can do both laminar and turbulent flow. Heat transfer, which is going to be used in this particular analysis, can also be done. Rotating regions, think of an internal fan, think of a centrifuge-like structure where the entire region is rotating. Think of impellers, where the inlet and the outlet may be facing different directions. You can do that as well. 2018 had one of the best enhancements in 2018 was the introduction of free surface flow. You can look at, let's say, a cylinder filling up, and let's say in the back of a truck, you have some liquid that's sloshing around because of the truck going at a certain speed. You can do compressible flow, you can do non-Newtonian fluids, and considering that Flow Simulation is a CAD integrated tool completely built inside of SOLIDWORKS, and so is SOLIDWORKS' simulation tools, the FEA tools. Result exchange can be done where we can export the pressure and the temperature distribution from Flow Simulation to a structural analysis. So if you're worried about the thermal profile and you want to know whether because of a specific thermal profile there's going to be too much warpage or not of your part, you can go ahead and export these results to SOLIDWORKS simulation and find that out. Also, time dependent analysis, which means you can do a steady state or a transient analysis and look at the response of your system at different time intervals. What does that mean? You want to make sure that your CPU can be used for 2 hours, 5 hours, 10 hours, 20 hours, right? And hence our problem right now is a steady state problem, because if we don't want the CPU or the thermal and the thermal profile to be acceptable after just 2 hours of usage, right? And if that was the case, we could have done a transient analysis to check the response for the first 2 hours only. But what we want is a steady state response for complete time. We're also going to use some advanced features today, like we're going to use the PCB generator. We're going to use the extended database for some fans. There is an add-on module above Flow Simulation called Electronics Cooling, which can be used as well. And this electronics cooling is specific to the electronics cooling industry, and I'll be talking about a few of the features that I use that's only part of the electronics cooling. But again, you want to think of heat pipes, joule heating, PCB generator, 2 resistor components, and a few other features like that. Okay, so let's go ahead and switch to SOLIDWORKS and take a look at what we have. So here is SOLIDWORKS, and I have a few configurations defined here. You can see the electronics enclosure on the outside. Here's my 2 slots, which I'm going to have as open vents. And we have the fans blowing in from here. And then we have some exits on the back end with circular holes on them. Here is my CPU with a heatsink above it. We have some capacitors. We have some more PCB boards over here and here in the bottom. And there are also some RAM components in the back. We have some ICs stacked up here and some mini heat sinks as well. So I'm going to quickly take you through the setup wizard, which will help set up the majority of the analysis. As you can see, I do have a bunch of studies already set up here, which I'm going to show you the results of, but I wanted to quickly show you some of the setup items as well. So let's go to the wizard, and even the most advanced users use the wizard in SOLIDWORKS Flow Simulation. I'm just going to call this Electronics Enclosure. Units are important. Again, there's a whole bunch of different units. You can select SI, but you probably want temperature to be in Celsius. And you can also save these units so that the next time you come in, you can use these saved units so that you don't have to set this up every time. And then we come to one of the most important pages of the wizard, which is what physics you want to include in your analysis. We spoke about internal or external flow. In our case, we have the fluid flowing inside the enclosure. So we have an enclosed computation domain, which means I would select the internal analysis. I also have heat conduction in solids, so we want to make sure that is checked. If you want to do a conduction only problem, then we check the next box as well. Radiation is another important concept. If you feel your results are going to need radiation effects to take into account, you can go ahead and include that. If the effects of radiation is relatively minimal as compared to the conduction and convection, then feel free to ignore that. Once again, transient or steady state, that's what the time dependent does. We are doing a steady state analysis, so I'm not going to check that. Gravity is important, and I wanted to take a moment to discuss this, because if you have free convection, where some regions are going to get hot and others are not, the hot air is going to become less dense, and because of buoyancy effects which need gravity is going to rise. If you do want to take free convection effects into account, then you do have to check gravity. In our case, since we have some forced convection, we have a fan blowing air from one side to the other. Typically, forced convection takes out about 10 times more heat than free convection. So while I'm making an approximation by not checking gravity, I'm doing a first pass analysis to compare multiple designs, and hence I'm not going to check gravity in this case. We have rotation and free surface as well, which of course we do not need right now. What is my default fluid? Of course, in this case we want to pick air. Like I said previously, you have non-Newtonian fluids as well. And continuing on, what's my default solid? So I'm going to go to my IC packages and select a specific chip array. I do want to emphasize that if you have a custom fluid, if you have a custom solid, you can go ahead and enter your own proprietary material properties in there that you can take into account, and obviously that stays within your database. It doesn't get shared with anyone else. But that's important to know, that if you have the material properties, you can go ahead and create your own materials and run your analysis with respect to that. There's some default roughness parameters which I rarely change, and then a default initial condition, which so all my parameters are going to start from what this says and then go on to what the final value would be for a steady state condition. Okay, so typically I would hit finish and then continue the rest of the setup. In this case, I'm going to hit cancel and then show you what we already have in store. So other than the wizard, a few additional things that have gone in on the setup. We have more material parameters that have been specified for everything. So any part that is not the default solid material that we picked in the wizard needs to be added on. So for example, here is my aluminum heatsink that I have selected. We have some polyurethane components, and everything that is not picked except the PCBs, I'll talk about the PCBs in just a second, are entered here. Okay, All right, so next up I want to talk about boundary conditions. I have some open ends in the back. I also have 2 slots on the top. So those are just selected and exposed to the atmosphere, but there is more to that. We've entered what's called perforated plates, and there's circular holes that have been defined in the back, and there's slots that have been defined on the top. Now what does this mean? So first off, the holes in the slots are going to add some resistance for the air to escape from these 2 areas. If I actually modeled all the holes in there, it would be computationally very expensive to actually mesh them and run them, which would mean my time exponentially increases. But from a flow simulation perspective, I just want to simulate the effects of those. So here is a slot that has been defined, and I went ahead and defined them myself. But in here, we can specify what's the hole shape. For example, here it's rectangular. What's the size of each hole? And based on those numbers, it's automatically going to calculate what the free area ratio is. That's a complicated way of saying what's the amount of open areas compared to regions that are closed. And this will automatically add some amount of resistance to simulate the effects of that perforated plate. And that way you're going to save a lot on computational time, but still getting the effects of that perforated plate. Okay, so that's that. We have some heat components that's been defined. Everything that produces heat is going to be defined. Let me go ahead and show you the fans as well. We have 3 external fans that have been defined, and the electronics cooling module is going to give you an extended fan base. So that gives you a more precise understanding of how different fans are going to work. I'm going to go ahead and hide the outside, and again, here's all my different components. I wanted to add a couple of I wanted to talk about a couple of additional features. These are part of the electronics cooling module that I spoke to you about. The first one is my PCBs. Typically, you're not going to manufacture the PCBs in-house. You're going to purchase it from an external vendor, and for that, we don't really need to model all the different layers of a PCB, and we just need to know the thermal conductivity values of it. So this PCB board generator helps me do that. I also have a 2 resistor component which I have specified for the CPU. If you look at how I've modeled this, it's just 2 rectangles that match the outer dimensions of what my CPU is that's producing the heat. But I don't have any other details, and we'll be talking a little bit more about 2 resistor components, but this gives me a good idea of the outer shape without getting into the nitty-gritty details. And as you see here, there's a little bit of simplification that's done to make a simpler model, but at the same time, we don't want to lose details on the amount of heat produced, the direction of the heat, and other important parameters like that. Goals are extremely important. When we started the webinar, we spoke about a few criteria that have to be met, and those can be specified as goals. For example, the maximum temperature of my CPU, I want to make sure I specify that as a goal so that flow simulation knows that that's something I need to converge to before I can stop solving and give the user an answer. So that's important, right? We also have some local mesh control that's been defined on those slots so that it has a finer mesh and we can understand the impact of it. So obviously I've already ran this study beforehand. It took about, I believe, 20 minutes to run. Let's go ahead and look at the details. So this one took about, close to 20 minutes to run this, and I want to quickly talk about the results. So let's go ahead and look at some of these results. Here is a cut plot that shows you the temperature distribution, and the lines show you the direction of the flow. So a lot of regions like these where you have recirculation is typically not good because you want the air to continuously circulate so that new cooler air is coming in and taking out more heat from the system. Okay, of course, getting some of these vortices are inevitable, but there is a possibility to try to avoid this by strategically placing different components inside the electronics enclosure. The everyone's favorite flow trajectories can also be seen, where we look at an animation of how the fluid flows from one area to the other. You can see all three fans working, and you can see the direction of the arrows. It picks up heat as it goes above the heatsink, and then you can see that it goes through some of the other components as well, the RAM, the IC packages, and all of that. We can hide the outside component and look at the insides as well. There's pretty uniform flow above this region, which is good. So let's go ahead and look at a few other outputs. Volume parameters is important. So for example, the CPU temperature, we can go ahead and look at what that is. So we wanted a temperature below 69. This has a maximum of about 43. Similarly, the IC packages has a maximum of about 88, whereas we wanted it to be below 95. And lastly, the RAM temperature is also around 45 degrees is the maximum. Okay. Now all of this information can also be exported to Excel. So goal plots is what we did before, and I'm going to quickly export this to Excel to show you the breadth of information that's available. So this tells us all the different goal parameters that we had, what are the values, how long did it take to converge to them, what were some of the default convergence criteria that it used. So for example, some of these high temperature packages, if we wanted a tighter tolerance, if we wanted a more precise value, we can go into the advanced settings of this and change that to something a lot lower, and then we'll get a more precise answer that might take a little bit longer to run. You see a lot of charts here. If you go to one of the other charts, you can see how a specific value converged to a temperature, and if you see a lot of chatter here, then you know that you probably want to run it a little bit longer, or run few more iterations with a tighter criteria, so that you get a more precise answer. So once again, I have ran a bunch of different studies, 11 to be precise, and we looked at three different configurations. But even in the different configurations, I can look at one fan on the right, one fan in the middle, one fan on the left, 3 fans. What if 2 fans were turned on? How are all of these going to affect my results? And that's what a simulation tool lets you do. It lets you quickly iterate between different iterations or different designs to get the best design that you can then take for testing, and hopefully reduce the number of iterations you have before you reach a final design. So to compare the rest of the designs, I want to take us back to our PowerPoint. And the first one was whether we want venting on the top or not. So in both of these cases, without any slots on the top, the temperatures were a little bit higher. But what we did notice is that it is below the allowable limit that we had set initially. So while the temperatures are a little bit higher, it's okay, and that just probably means less manufacturing operations to create those slots on the top. Similarly, fan power consumption, right? I don't know if you guys can hear my CPU fan running right now, but you typically want the fans to consume less power, right? So here is a comparison of 6 different designs with just 1 fan or 2 fans turned on, and you can get a comparison of the different temperature profiles in each of those cases. Okay. So of course, in this case, when you have fan B and C turned on, where it goes directly above the CPU, that produces the least temperature profile amongst all 6 configurations. And lastly, heatsink performance. So in this case, we had 2 different designs for the heat sinks. One was with the pins, and what we saw was the external fans with the slot with a slit heatsink design produced the best results in our case. So I wanted to quickly take a moment to talk about some of the advanced functionalities that we used. So once again, electronics cooling, the 3 advanced functionalities that we used in this specific analysis. One of them was the 2 resistor components. So 2 resistor components are typically a lot more complicated. We simplified them with just 2 rectangular extrusions, which I will be talking about in just a little bit. We also simplified the PCB generator, and lastly we looked at a simplified fan by just providing the inlet for it, and all the specifications of the fan was already part of the extended engineering database that we have inside Flow Simulation. So the 2 resistor component. First off, these are typically very complex, and what happened was it gets relatively hard to simulate the effects of this. So the Joint Electron Device Engineering Council, or the JEDEC standard, was developed a few years ago, where you create a much more simplified model with just 2 rectangles, and you specify the resistance of the chip, the junction, and the board, and as long as you provide the exact dimensions of the rectangle that matches the CPU or the package that you're trying to simulate, what it does is it automatically provides adiabatic walls on the side, which means no heat transfer lateral to the direction, and all the heat is transferred either below to the PCB board or directly above, where in our case we had a heat sink above it. So it's an idealized model that is a good representation of what happens in reality, but without adding all of the details of your component. Another one is the PCB layer. Again, in most cases, you're not going to be making the PCB yourself. So as long as you know the amount of dielectric constant, as long as you know the amount of conductive material in there, let's say you have 5 layers, 10 layers, 50 layers, as some of the boards have these days, you would get an equivalent thermal conductivity value for that PCB using the PCB generator tool. And what that does is it helps you get a good understanding of the thermal profile without going into all the nitty-gritty details of what it does. Another one that is available with electronics cooling is joule heating. Now, joule heating is something we do not use in this specific analysis, but what joule heating does is it can look at the amount of heat produced because of a current that is passed through the different components. So if you have low current or high current, you can look at a thermal distribution of it and the amount of thermal heat that it produces and dissipates to the rest of the enclosure. And lastly, heat pipes are extremely complicated, and what they involve is they involve one region that has a fluid that evaporates and becomes a gas or becomes a vapor. Why is this done? Because the latent heat of vaporization takes in a lot of heat without much change in the temperature, which is very advantageous from a electronics cooling perspective. So above the heat sink, you're going to see it collect heat and become a vapor, and then go to the region where it needs to dump that heat and then cool down and return back to a liquid state. So because of this phase transition, and phase change cannot be done in flow simulation, so heat pipes is one way to approximate that. If you have heat pipes, would be a good way to approximate the behavior without getting too detailed or adding too many computational elements in your design. So once again, just to sum up the entire analysis, we quickly simulated 11 different designs and compared them, and for an electronics enclosure, and what we did was we looked at the different thermal distributions, we looked at the different outputs available to us, and we went from there. So once again, I would like to thank you for your time.